Okay, so now we will continue in earnest in chapters 9 and 10, and primarily we're going to go work with the chi-squared test. Okay. Okay. And the first type of chi-squared test is going to be called the Chi-Squared Goodness of Fit test. Okay. And again, everything we're doing today, or not everything, chapters 9 and 10 are all about categorical data. So here we have a situation where we have proportions in mind, okay? So our null hypothesis is we've got proportions in mind about the data. Okay? And generally we have more than two categories, okay? I mean, you could have a chi-squared goodness of fit test with only two categories. Actually, I shouldn't even say that. Yeah, you can use a chi-squared goodness of fit test with two categories or more than two categories. It doesn't matter, okay? You got proportions in mind about the data, and we have data, and we want to see how good or how well does our data, or how well does the proportions we have in mind fit the data, okay? We have data, and we ask, how good is the fit between these proportions and the data? Okay. So for example, if you roll a fair die, what would you expect? You would expect each side to show up with equal probability, okay? Okay, so in essence, the proportions that you have in mind are the probability of getting a 1 is equal to 1 out of 6. Probability of getting a 2 is 1 out of 6, so on and so forth. So that all 6 sides, probability of getting a 6 is also 1 out of 6. Okay, you're expecting all 6 sides to have a probability of showing up of 1/6. Okay. Let's say this is the data that you have, okay? Oops. Okay, so this is the face, and this is the count that you get, okay? So if you roll it 100 times, let's say you get, I'm going to have to do some math here. 15 plus 14 plus 20 plus 16, and let's say we do another 15 and a 20, okay? And if this shows up here, if these are the results of 100 die rolls, is this cause for concern? That's what we want to know, okay? You're expecting 1/6, so you're expecting around 16.6 of each number, but we didn't get that, okay? Okay, so then we would ask, does this data contradict the proportions? That's what we want to know. That's the Chi-squared goodness of fit test. We've got proportions in mind. We're expecting certain things, and in this case the proportions happen to be all the same for a fair die, but it's not necessarily the case. And your data looks like this, and you want to know, well, how good is the fit between these proportions and the data? That's why we call it the goodness of fit test. Okay, so does this contradict? Okay. Maybe another example, and maybe we'll use this one as our problem, is that maybe so if you study biology, right, and you have like this Punnett square, right? Here, let me actually start a new. So, oh yeah, how do these things work? Let's say you've got like you've got big X and little x, and you're breeding with big X, little x, or something. Is that the Punnett scores? Or do we not use X? Do we use a different letter? X and Y are reserved for our sex-defining chromosome. Maybe we'll use. Is it? Yeah, A and we'll just use. Yeah, we'll do this. Okay. So we'll do this. Okay. And then so you have this and you have this, right? Okay. And so what you're expecting, 25% to be AA, 50% to be A little a, and 25% to be that, right? I'm out of my element here, so okay. And so let's say you looked at the progeny of, I don't know, whatever, a whole bunch of these things, okay? And so this is the data that you have, all right? Maybe you encounter 54 AA and 97 A that, and 49 this, okay? Does this data match that? Okay, this is essentially what we're asking. Does the data and the proportions, I should say do the data and the proportions fit? That's essentially what we're going for. Okay. So when we do this, our null hypothesis would be that the proportions that we have in mind that are correct. Okay, because we're talking, the hypotheses are always about the population, and so the null hypothesis would say, the population is defined by these proportions. Specifically, probability of AA is 0.25, probability of that is 0.5, and that is that, okay? So your null hypothesis states that the population is defined by these proportions. And the alternative, okay, if you have more than two categories, the only thing you can say is that at least one of these proportions is incorrect. Okay. And obviously, if one of these is wrong, then that means the other, something else has to be wrong. But when you have more than two categories, it's hard to say, okay? Because let's say we were saying this number 0.25 is too small, then that means between these two other categories, the numbers are too big, okay? But it's hard to say who goes what and what goes where. So the alternative is just that at least one of these proportions is wrong. And so here's just a little note. If you have more than two categories, the alternative hypothesis will always be non-directional. Okay. You can only have a directional hypothesis if the alternative hypothesis, if you only have two categories. Okay, you can only have a directional alternative if there's only two categories, like male and female, or something like that. Okay. So how do we test the fit between our data and what we expected? Okay. So we will go through calculating or doing the actual test. All right, so the chi-squared statistic is defined by observed minus expected squared over expected. Okay, and then we add this up for all categories. All right. So remember the expected proportions were 0.25, 0.5, and 0.25 for each of these things. Let me just say that, and I forgot. 54, 97, 49. Okay, and what we observed counts. So I'm gonna leave a little blank spot. This is going to be expected counts. Okay, the observed counts, and I just forgot already. 54, 97, 49. 54, 97, 49. Okay, so we observed a total. How many things do we observe? 54 plus 97, I think, adds up to 200 exactly. Yeah. Okay, so we observed a total of 200. For the expected counts, we're still going to have 200, but what would we expect? We would do 200 times 0.25, and we would expect to see a total of 50 big A, big A. We would expect to see a total of 100 big A, little a, and I would expect to see 50 little a, little a. Okay? And everyone's okay with getting the expected counts, right? All right, and so all we do is we just go observed minus expected divided by expected for each category. So I just do 50 minus 54 squared over what I expected. Oh, so I did this actually wrong. Sorry. The observed was 54. It doesn't matter because you're squaring, but just so I'm meeting the proper equation form. Okay, so we're just doing observed minus expected quantity squared over expected, and we're doing that for each of our categories. So I get 4 squared over 50 plus 3 squared over 100 plus 1 squared over 50 . Okay, so 16 over 50 plus 9 over 100 plus 1 over 50. So I get a tiny little number, 0.43. So my chi-squared statistic is 0.43. Is that okay? So far so good with everyone? Alright, so just like everything else, once you have a test statistic, we're going to go to the relative reference table. So, I'm sorry, when we go to the table, we need the degrees of freedom, okay? And so the degrees of freedom for the chi-squared test, or chi-squared goodness of fit test, is the number of categories minus 1. So in our case, 3 minus 1, I've got 2 degrees of freedom. So my chi-squared statistic is 0.43. My degrees of freedom is 2. Okay, and so my tail probability is going to be, whatever it is, it's more than 20%. Okay, because the very first number is 3.22. So 0.43 fits right there. Okay, so that means my tail must be greater than 20%. Okay. And if you read the print at the top of the chi-squared table, it says column headings are for non-directional p-values. Okay, so if the alternative is directional, which is only possible when degrees of freedom is 1, the directional p-values are found by dividing the column headings in half. Okay, so we have a non-directional test, so the tail area is the p-value. So my p-value, whatever it is, it's more than 20%. So if we go back a slide and we look at what our hypotheses were, the null hypothesis was the population is defined by the proportions. Population is defined by these proportions, yada yada yada. And then the alternative is at least one of these proportions is wrong. Okay. And so with my p-value being greater than 20%, our conclusion is do not reject the null hypothesis. And we would say we have no evidence to believe that any of these proportions are wrong. Any of the defined proportions are wrong. Yes. So if we had a situation where, you know, if I was expecting not 25% here, but if I was expecting something else, 40% to be big A, okay, then my expected count here would be 80, right? 80 out of 200 if I'm expecting 40%. And then my statistic would be much bigger, and when I look that up, I would get a much smaller p-value. And that would indicate that at least one of the proportions that I have in my equation, or that I've defined, is wrong. Okay. Okay. Is that okay? So we're going to do an example here, and this is one of my favorite examples just because I find it so fascinating. And this is going to be an example with a directional alternative, okay? So a directional alternative requires that we have only two categories. Okay, and so if you wanted to use a directional alternative for, let's say, rolling a die, the only way you could do it would be you'd have to pick one of the faces, and that would be the thing that you're investigating, okay? So one way you could see is if a die is fair is you just roll it and you see if all 6 numbers show up approximately equal, and you would use a Chi-squared goodness of fit test, the regular kind. But you could do a directional alternative, but then you'd have to say, you'd have to choose one of the sides, let's say the side 3, and you'd say, I think this die shows the side 3 too often. And you would have to do a test to see if the side 3 shows too often. Okay, that would be the only way you could do it. Okay. Well, anyway, this is a different test, and the researchers wanted to know if people could postpone their death, per se. Okay, it's a little strange, but it was rather brilliant the way they did this research. Okay, so they wanted to know if people who were at risk of dying could somehow postpone their death. Okay, so they looked at a whole bunch of elderly people. Okay, and they wanted to see if there was they found basically what they did was they looked at all these elderly Chinese women, and they looked at the Harvest Moon Festival, because the matron, or the elderly Chinese women, played an important role in the festival, and so they would have a reason to try to, quote, postpone their death. And they picked the Harvest Moon Festival because that thing moved. It was not the exact same time from year to year, and so it would not be confounded with annual changes and things like that. And so they looked at a whole bunch of people who died within 1 week of the festival. Those who died one week before the festival and 1 week after the festival. Okay, and so if in our case, the null hypothesis would be that that there's no link between the time of death and the dates of the festival. Okay, so the null hypothesis would say no link between death and festival dates. Okay, and so when they looked at the data, this is essentially saying that the probability of death before the festival would be the same as the probability of death after the festival. Okay. So is that okay?
Yeah.
All right, and so by having this, essentially we can also just write probability of death after the festival is equal to 0.5. Okay. These are all saying the same thing here. And then the alternative hypothesis, they suspected that through some means or another, these people are somehow able to postpone their death, okay? And the alternative would be that the probability of death after the festival is greater than 0.5. Okay? And so there were a total of 103 deaths that happened within 1 week of the festival. Okay. So let's do the expected. So expected proportions, expected counts, and we'll do the observed counts. Okay, there's a total of 103, and this would be before and after. So we're expecting half to be before, half to be after. So if there's a total of 103 deaths, we would expect 51.5 to be before and 51.5 to be after. Okay? It's fine that there's a decimal in your expected counts. Okay, your expected counts, they can have decimals. That's not a problem. What we observed was that there was 33 before and 70 after. Okay. So our chi-squared statistic would be 33 minus 51.5 squared over 51.5 plus 70 minus 51.5 squared over 51.5. And we would get a chi-squared statistic of 13.3. Okay. All right, so we have 1 degree of freedom. Okay, number of categories minus 1, and we have a directional alternative. So we go to so we go to our table and we're looking at 13.3, okay, with 1 degree of freedom, and we find that it would go right here, okay. So it's in between 10.83 and 15.14 for 1 degree of freedom. So our tail probability is between 0.001 and 0.0001. Okay. Because it's a directional alternative, I'm going to take this and divide by 2. Okay, and so this p-value is extremely small. So we would reject the null hypothesis. And this indicates, the data indicates, that that the proportion of deaths after the festival is greater than 0.5. Okay, and even though it's just an observational study and not an experiment, it would indicate that there's some evidence that maybe there's some ability to kind of postpone your death, okay? And we don't understand the mechanics or the exactly what's happening here, but the data suggests that the rate of death increases after the festival, and although we might not fully understand why, it's at least an interesting thing to note.
So they're trying to postpone the death till after the festival, otherwise they would have died before.
Right, because the elderly Chinese woman generally plays an important role in this festival, and so they would want to be alive for that. Okay. Who knows? Okay. It's just interesting, right? I'm not trying to say like something crazy is happening here. It's interesting that this is a pattern that we can pick out in the data. Technically, whenever you have a directional alternative, you should do a directionality check, okay? And I neglected to do that. How would we check directionality here? Here, the alternative says that the probability of death after the festival is greater than 0.5, which would mean that when we do our observed counts, the deaths for after should be greater than what we would expect under the null hypothesis. And indeed, that is the case. 70 is greater than 0.5, so our directionality check is met. Okay, so maybe I'll just write that. All right, so that is the Chi-squared Goodness of Fit test. You have some exercises in your homework, and you can do it for multiple categories or just 2 or whatever, and that's it. Okay. Maybe I think the hardest part with a with a Goodness of Fit test is figuring out your expected proportions if they're not stated explicitly in the problem. Okay. So if the expected proportions are not stated explicitly in the problem, you're going to have to kind of read through the problem to try to figure out what your expected proportions are, and then you can get your expected counts. So it might say something like, you're playing a game of chance, and whatever, you roll a die, and if you get the numbers 5 or 6, you win, okay? Well, then your expected probability of winning would be 2 out of 6 or 1/3 or something. So read the problem carefully to figure out your expected proportions, and based on that, then you get your expected counts by looking at the total number of observed counts that you have. Okay, is that all right? So we're going to move on into Chapter 10, and the book splits this up into Chapter 10, but in my opinion, they're all related. This is the chi-squared test for independence. Okay. And here you've got 2 categorical variables, okay? Chi-squared test for independence, essentially you have 2 categorical variables, and you want to see if there's a relationship between them. Okay. This is in contrast to the Chi-squared Goodness of Fit test, where you just have 1 categorical variable and you have proportions in mind. Okay, so that one you just have 1 variable and you have preset proportions in mind that you're testing. Here you have 2 variables. You don't have any proportions in mind. You just want to see if there is a relationship between the variables. Okay. All right, so here's, oh gosh, I'm trying to think of a good question to put here. All right, so here's an example. Okay, okay, so is gender related to how likely someone is to have taken an HIV test? Okay, so this is data from an older study. So I think the numbers would be different today. But in this study, we're looking at gender, male and female, and did you take an HIV test? Okay, so it's not whether someone actually has HIV or not, but it's just test or no test. Okay, so under our null hypothesis, the null hypothesis would state that the two variables are independent. And I'm going to just leave a little gap there. And then the alternative would say that there is a relationship between the two variables. Okay. So when it came to probability, how did we express variables being independent? So I would say that the probability of being male given we'll say taking the test, if gender is independent of the test, of having taken the test or not, this should be equal to what? Probability of, okay, it could be equal to probability of male, or it could also be equal to probability of male given no test. Okay, so this is one way. There's many ways to state the null hypothesis, and this would be one way to do it. Okay, another way is you could say probability of female given test is equal to the probability of female given no test. That would also be a fine way to do it. Okay, what about this? Probability of male given test, is that equal to probability of female given test? Would that hold? No. Okay, this would only work if their probability of male and female were exactly the same in the population. So this is not a valid way to check for independence. Okay, these ones are okay. Also okay would be probability of test or no test. Test given male, is that equal to probability of test given female? Okay, these are all different ways to express two variables are independent symbolically. Okay, relationship between the variables, whatever you used in the null hypothesis, just change that. Okay, so if you did female given test, then say female given test does not equal whatever you might have. So let me put down the observed data. Okay, so the observed data, we have females, males, taken the test or no test. We had 61 here, 59 here, for a total of 120. 9 females took the test, 52 had not. 8 males had taken the test, 51 had not, for a total of 17 have taken the test, 103 have not. I feel like today, anytime you get your blood drawn, they automatically just test it for HIV. So I think these numbers are going to be different should this the study be done today. But this is the results of the study here. Okay. So this is what we observed. Okay, and the question is, well, does this indicate that in the general population there is a link or no link? Okay. So if there was no relationship between gender and having taken the test, if the two variables are independent, what would we expect? So actually, let me do this on a second slide here. I'm going to just copy this. Okay, let's talk about what we would expect. All right. So I'm going to just keep the total rows the same, okay? Okay. So if the variables are independent, then another way we could state this is that we would say that the probability of A and B would equal the probability of A times the probability of B, right? So if we look at let's look at this first cell here. Females who have taken the test. If we just look at the total columns over here for our observed data, what is the probability that we randomly select a female? It would be 17 out of 120. Okay. And if we look at the probability, I'm sorry, not females. That's a probability of having taken the test. I'm writing all this incorrect stuff. Okay, so 17 out of 120 people have taken the test. And what's the probability that someone is female? If we randomly select someone out of the 120, 61 of those are female. So we'd have 61 over 120. So then the probability that someone has taken the test and is female would equal 17 over 120 times 61 over 120. This would be the probability of ending up in this cell if they were independent. Is that good? Okay. So that's the probability of ending up in that cell if I have a total of 120 people, how many people would I expect to end up in that cell? I would expect n times p, right? N times that probability. So the expected count would be 120 times whatever this probability is. Probability of being test and female. So my expected count would be 120, and I'm purposely leaving everything as a fraction here, times 17 over 120 times 61 over 120. Is that okay? So far so good? All right, so what we see is that this cancels out and this cancels out, and we're left with 17 times 61 over 120. Okay? And so the expected count, the overall, for any of these cells is going to be, let me just write, the expected is going to be the row total times the column total divided by the grand total. Essentially, you're saying 17 out of 120 times 61 out of 120 times a total of 120 people. So we're expecting this probability to end up in this cell, and if I multiply that number, that probability, by the grand total number of people observed, this would be how many people we expect there. Okay, so doing that, 17 times 61 divided by 120, I'm expecting 8.64 people to be females who have taken the test. Okay, and I can do that for all three other cells, but also if I have 8.64 here and the row has to add up to 17, what number has to go over here? 17 minus 8.64, which is 8.36. And if 8.64 goes here and this thing has to add up to 61, what has to go here? 52.36. And if this and this have to add up, the number that goes here would be 50.64. Okay? So actually, once this number was determined, the other three were locked down. Okay? You could go through and do the math for each of these, but really, once this number was determined, the other numbers were locked down. Okay? And that actually illustrates the degrees of freedom. How many degrees of freedom would we have in this situation? We only have 1 degree of freedom, okay? Because once this number is determined, the other 3 numbers had no choice, okay? So in this situation, we have 1 degree of freedom, okay? And degrees of freedom, when you're doing a chi-squared test for independence, is the number of rows, so I'm just going to write n row minus 1, times the number of columns minus 1. So in our case, we have 2 rows and 2 columns. Don't count the total columns. Okay? We have 2 rows, 2 columns, so we have 1 times 1, 1 degree of freedom. Okay? Don't count the total columns in the number of rows. Okay, so we have our expected counts, we have our observed data. Now we can get our chi-squared test. So let me just, or chi-squared test statistic. So let me just copy that, save this. No, that copied. And we can get the, so our chi-squared statistic is going to be observed minus expected quantity squared over expected. Okay, so we'll do this for all four cells. We do 9 minus 8.64 squared over 8.64, and you just go through.
For the DF, if you're counting the columns, you don't count the total columns?
Yeah, do not count the total columns when getting the degrees of freedom. Okay, so you have 2 rows and 2 columns. A neat little thing is that when you have 1 degree of freedom, the numerators all end up the same. Okay, the denominators are different, but the numerators all end up the same. You have 0.36 squared for each of these. That only happens when you have 1 degree of freedom. So I'm going to do that. 1296 over 8.64 plus that over 8.36 plus Alright, okay, so my chi-squared statistic is very, very small, 0.0355. Okay, so if we go to the table, looking up 1 degree of freedom, this time, and we're looking for the value 0.0355, we'd see that it's much closer to 0 than 1.64. So our p-value, whatever it is greater than 20%. Okay. We had a non-directional alternative, which was just saying that there is some kind of association. And at this point, looking at this data, we see no evidence to reject the null hypothesis. All right. Okay, so our data does not support the alternative that there is a relationship between gender and having taken the HIV test. Okay, so just a recap. Chi-squared goodness of fit test, you have 1 categorical variable and proportions in mind. Chi-squared test for independence, you have 2 categorical variables. You're going to create this type of two-way table, and you're seeing if there's a relationship between the 2 categorical variables. Right? So your biggest indicator is just as you're reading a problem or whatnot, ask, do I have 1 variable and proportions, or do I have 2 variables when we're dealing with categorical variables, and am I looking for a relationship? Okay. In terms of calculating the chi-squared statistic, it's the same. Observed minus expected squared over expected. So that part's straightforward. The important part is the setup, which is determining your hypotheses and recognizing when you have a goodness of fit test versus a test for independence. Okay, we'll end there.